Hello guys, welcome back to TechDose, and in this video we will look at length of longest Fibonacci subsequence, which is from Leetcode number 873. We will look at three approaches here. The first one will be simulation, second one is going to be binary search, and the third one will be dynamic programming approach. Let's look at the problem statement. In this problem, a sequence x1 to xn is Fibonacci like if n is greater than equals to 3, and if you add up xi plus 1, then you will be getting a value equals to xi plus 2 in the particular subsequence, right? Where I plus 2 must be less than equals to n. That means within the bound of the array. Given a strictly increasing array of positive integers forming a sequence, return the length of the longest Fibonacci-like subsequence of array. If 1 does not exist, then return 0. In this case, they are mentioning about strictly increasing array means two different values will not be same, and it is already sorted in ascending order, right? A subsequence is derived from another sequence array by deleting any number of elements including none from the array without changing the order of the remaining elements. For example, 3, 5, 8 is a subsequence of 3, 4, 5, 6, 7, 8, where you remove this 4 and you have to remove this 6 and 7 to get 3, 5, 8. So the order will be same, but you can choose not to pick some of the items in the middle, right? So according to the problem statement, what you can do is, given the array, let's take the first array. If I have to make a Fibonacci like sequence out of it, then I have to always make sure that for a given sum value, there is always an a value and b value on the left hand side, so that a and b sum up to give the given sum value. Like in this case, if you take 1 and 2 on the left hand side, then 3 will be equals to 1 plus 2, and that will be equals to 3. Now this chain has to be actually increased. So the next element, if this happens to be x, then this x must be equals to 2 plus 3 if it belongs to the same Fibonacci chain, right? So do we have a 5 here? Yes. So 5 will be next in chain after 1, 2, 3. So if you have to find such kind of sequence, Fibonacci like sequence, and that too of the longest length, then you can try generating all possible subsequences. So for any array of size n, if you try to generate all the subsequences, then each of the item will have two choices. Either you include it in the subsequence or you don't include it. So since each of these items will have two options, if n items are present, then the total number of subsequences that you can form can go to 2 to the power of n. And out of these 2 to the power n different combinations that you get, one of them will definitely be returning you the answer, right? If there is any Fibonacci like subsequence. If there is none, then the question was asking to return 0, right? Now if you look at the array length, then can we write a 2 to the power 1000 in terms of complexity? Well, absolutely not, because if you consider 2 to the power 20, we can assume it to be 10 to the power 6, which is within the limit of 10 to the power of 8. But if you consider 2 to the power 30, it will go to 10 to the power of 9, which is beyond your 10 to the power 8. So 2 to the power 30 will also give you TLE. So how can 2 to the power 1000 even run? So this complexity definitely will not pass. We have to do something better, right? So I hope the problem statement is clear. Now let's look at the simulation approach of solving this entire problem. So this will be kind of a greedy simulation. And here what we do is, given the array, I have taken 6 items from 1 to 6. I have to find the longest Fibonacci chain. So what I have to do is, I will be choosing two items A and B. A will be on the left hand side of B. So for every A, I will try for all the B's on the right hand side of A. Therefore, let's start with the A assumption being 1 and the B assumption being 2. So I have to find out a given sum value which can extend this Fibonacci length. Okay, so Fibonacci length will start with 2 because we are assuming A and B. Now I have to find out if there is an A plus B to the right hand side of B, because this array is strictly increasing. So definitely if you have to find A plus B, given the index of A and B, it must be always to the right hand side of B, isn't it? Because it is strictly increasing. So we have to find A plus B. So one approach is to just iterate over this entire array and find it linearly, which is not a good approach. Rather, if you had actually put all these items into a set, then it will be far more easier for you to search for any given value. So I will insert all these items into a set, right? And after that I will be just searching for a plus b. So do we have 1 plus 2? Yes, we have 1 plus 2. So yes, we can actually extend this length by one more size. So what I will say is the Fibonacci length can be increased by 1, and so the Fibonacci length can become 3. Now since we could increase this length, our longest length will be again reassigned to a new value, which is 3, right? And since we know that in a Fibonacci series, if you have a comma b, then the next value will be the sum of a plus b. Now when you extend it to x, then this value can be assumed to be a new a, and this value can be assumed to be the new b. So that is how we will be doing it. If you find the sum, okay, it will be a plus b. Now the new a value will be the previous b value, and the new b value will be the previous sum value, so that I will be calculating the new sum. So what is your new a value? It will be actually 2, isn't it? It will be 2. And the new b value, it will be 3, whichever was the sum value. Now you have to find out the new sum value, which is 5. So do we have a 5? You can just find it in the set. Yes, we have a 5. So the Fibonacci length will increase by 1. And therefore the longest will also get updated, longest chain length, right? And now again we will update these values according to this piece of code. So the new a value will become 3, the new b value will be the sum value, and the new sum value will be 8. So do we have an 8? We do not have an 8, right? So this is where our chain will break. And therefore by starting the chain with the first element being 1 and the second element being 2, our maximum chain length of Fibonacci like sequence was 4. Okay, now we will not just stop here, we will have to try this for everybody. So now we will increment the b here, and then we will try 3 to be the next item. So if you take 1 as the first item, 3 as the next item, then you can say that 1a is 1, b is 3, so the sum value will be 4. So do we have a 4 in the set? Yes, we have it. So again the Fibonacci length initialized with 2 will become 3 now, right? Now 3 will be compared with the longest length. It is already 4, so no update is going to happen. Again you have to update this a to the b value, the b to the sum value, and the sum will be assuming a plus b, which is 7. So find out 7. 7 is not present in the set, so this is where it will break. And what was the Fibonacci length that we could find? It is 3, isn't it? So again we have to repeat the process. If you repeat it for 1 4, the next item will be only 5, but after this it will not extend, so Fibonacci length will only be 3. If you extend with 1 5, it will be just extending to 6, which is length 3, and we cannot actually take this 1 and 6 because there will be no next item. So we have tried all the possibilities starting with 1. Now we will be trying all the possibilities starting with 2. So if you take 2 and the next item to be 3, then you will find that the Fibonacci length will be 3 maximum, which is 2 3 5, and beyond this you cannot extend because 5 plus 3 will be higher than 6, right? And you can just keep on doing this. With 2 comma 4 you can go to 6, but not beyond that. And again if you try all these possibilities, it will take you order of n square combinations, right? Why n square? Because for the first item being at index 0, we are trying with every other item as the second item, and then again we will be shifting our first item, assuming it at index 1, then we will be trying for all the n minus 2 items, right? So this is the sum of 1 plus 2 plus and so on plus n minus 2 or n minus 1, you can say. So these many comparisons will happen, which is equivalent to order of n square, right? So that is why there are order of n square such starting pair. Now we have order of n square starting pairs, which is a comma b, initializing a comma b, but we are also trying to extend it by a chain length, by a Fibonacci like chain length, isn't it? So what can be the maximum chain length? Well, Fibonacci like sequence is actually an exponentially growing function. So if you consider an exponentially growing function, the reverse of it will be a logarithmically decreasing function, right? Or you can say that the number of steps in an exponentially growing function to reach from 1 to n will always be log of n. Okay, so in this case, since the Fibonacci series do not just depend on the length of the array, it depends on the maximum item. Okay, if you think about it, you will get it. Therefore, the time complexity will be n square times log of m, where m is the maximum number, because you could have had the items as 1, 1, 2, maybe 3, 5, 8, 13 and so on, right? So it is not the length of the array which is defining how long it will run, but it will be defined by the maximum item. Okay, just for a simple comparison, if we have to find the Fibonacci numbers, not a Fibonacci like sequence but the actual Fibonacci series, from 1 to 10 to the power of 9 there will be only 44 items, and if you consider log of 10 to the power 9 base 2, it will be almost equals to 31, just like a 32-bit integer. Similarly, if you consider Fibonacci series from 1 to 10 to the power 18, it will give you 90 Fibonacci numbers, and if you consider log of 10 to the power 18 base 2, it will be almost 63, which is kind of a 64-bit integer, right? So simply, if a function grows exponentially, it takes logarithmic count of steps to reach from n to 1 or 1 to n. Any way you can count, right? So I hope this greedy simulation is clear. Let's now look at the code. In this approach, we are given the array, finding the size of the array and pushing all the items of the array inside a unordered set. Then after this, I am assuming a longest value equals to 0, which is the maximum chain length. And then I am trying for all the A and B pairs. So what I'll do is I will extract A and B and assume the Fibonacci length starting from 2, because A and B are already counted. And after that, I am trying to find the sum value. So if a given sum value A plus B is present, then this means that I can form a Fibonacci like sequence. So the sum value will become A plus B, and for the new sequence, the A will be assuming the B value, B will be assuming the sum value, and the Fibonacci length would have increased by 1. So after finding the chain length starting from this A comma B, then I will be updating the longest value, the longest Fibonacci like chain length. And after having tried for all the starting points, we can simply return the longest as our final answer. So this is the first solution. Now let's look at the binary search solution. In this case, we will be using the lower bound concept. So if you imagine about an array having these items 1, 2, 2, 3, and these are the indices, then if I apply lower bound on 2, then this will give me the first occurrence of an element which is greater than equals to 2, and that will be actually index 1. So it will return an iterator for index 1, or you can say index 1 itself. If I apply lower bound on 4, then it will be returning me index 4, which is out of bounds, right? If I apply, let's say, lower bound on 0, then it will be returning me index 0. That means this is the first occurrence of an item greater than equals to 0, right? So this is the concept we will be applying here. Now I will be using the same pair comparison in this case as well. So for every A item, I will be trying for all the B items on the right hand side, and I will try to maximize the chain length again. So let's say that my A value is 1 and the B value is 2. So my target is to find A plus B on the right hand side of B, because it is strictly increasing, right? So I can apply binary search on this, and I will try to find 3. So is there a 3? Yes, there is a 3. So I have successfully found it, right? So it will increase the Fibonacci length by 1. It will increase it by 1. So I'm not counting this first 2 initially, but if I can find A plus B, then I will do Fibonacci length plus plus. Now I will be reassuming my new A value to be 2 and the new B value to be 3. And again I will be solving this by using recursion. Now my new target sum will be 2 plus 3. My new target sum will be 2 plus 3, which is 5. So is there a 5? So I can again apply binary search on top of this, and yes, there is a 5. So I can increase the Fibonacci length by 1 again, and the new A value will now become 3. So I can just write a new A value to be 3, new B value to be 5, and the new target sum value to be 8. Now if you again apply binary search, it will go out of bound. So since it will be out of bound, therefore we cannot extend the chain length beyond this point. So I could actually increase the Fibonacci length by 2 items if I do not count the first 2 items. So in order to compensate for first 2 items, I will be adding 2 value to it, and so it will say that the Fibonacci length is 4. Okay, and after having done all this process, I will always be trying to maximize the longest length. So I will be updating this to 4. Now I have just shown you for one pair, but we will be doing this for all the pairs. We know that already the number of pairs will be order of n square, and if you are applying binary search for every search, then you know that it will be log of n where n is the total number of items. And from the previous approach, we know that the length of the Fibonacci like sequence will be log of m, where m is the maximum number. So this approach will be taking you order of n square log n log m. So this will have a little bit higher complexity, okay, but the good part is it has space complexity as order of 1 as compared to the previous case where you had order of n space complexity, right? So you can just weigh what actually matters for you. If space complexity is something that matters, then you can always choose the second approach over the first one. In the binary search approach, we are given the array and we are finding the size of the array. We are keeping the longest equals to 0, and then we will be trying with all the pairs of a comma b. And once we have taken a pair a comma b, then I'll try to find out how much I can extend from a comma b. So I'll be finding Fibonacci chain length, and this is the recursive function Fibonacci chain length, where I'll be taking a comma b and the size of the array, and I'll be finding the lower bound and check if the lower bound is within the bounds and the array at Fibonacci index, that means the lower bound is actually equals to a plus b. And if it is the case, then we are able to extend this a comma b to a new Fibonacci index, and that is why I will be adding 1, and this b will become the new a value and the sum will become the new b value. So you can see in the next recursion call I am passing accordingly. Otherwise, if I cannot extend it any further, I will be returning a 0. So if the extension length was greater than 0, that means I can actually extend it, and so this a comma b has to be accounted for. Therefore I will be adding 2 to the Fibonacci length. Otherwise, if I cannot extend it, then this will not run, okay, and at the end I will be returning the longest. So this is the binary search code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. Now, having looked at both the solution, let's now look at the dynamic programming solution. So in this case, again, I have taken the same example and I will be considering 3 indices A, B, sum. So these indices will be considered in left to right order in such a way that A will be less than B and B will be less than sum. And our array at A plus array at B should be equals to array at sum for all the sum indices greater than equals to 2. Because the sum index cannot be 1, because at least you should have 2 items on the left hand side, okay? So sum index should be starting with only 2. Right, so this is where the sum will start. Now I have to find 2 items, A and B. They must be 2 different indices in such a way that they sum up to give the given sum value. How to do that? Now since this array is already strictly increasing and you know a sum that you want to find, then we can reduce this problem to a 2 sum problem using the 2 pointer technique. Now let me explain you. Let's say that in this particular subarray, we were given a target of finding sum equals to 7. How do you find this? So I will be taking 2 pointer, a left pointer and a right pointer, okay? And I will be just adding these values 1 and 5. So the sum will be 6. You need to compare it with the target. If it is less than target, then I need to increase the sum, and therefore I have to increase this left pointer to the right hand side. Now you add this 5 plus 2, 7. So yes, I have found the target, okay, which is matching. So 6 is equals to the target. If you happen to find that, then you increment the left and decrement the right. Now again you check this 3 and 4. Again it is forming the target. So you can increment the left and decrement the right, isn't it? This is the technique, and if you want to know the details, you can follow my video on the 2 sum approach, right? The 2 sum problem has been solved with the 2 pointer technique. You can just have a look at it. Now in this dynamic programming approach, what I will be doing is I will be picking up the sum value, and I will assume that this particular index is the end point of a Fibonacci like sequence. And if I consider this 2 to be the end point, then what is the longest length of Fibonacci sequence that I can form here? So in this case, it will be equals to 3, right? And how it is 3? Because I can have 1, 2 and 3, right? Because the previous item of this 3 can be 1 and 2, and this is completely fine. Now I will repeat it for all the indices. What will be the endpoint for this 4? Now the endpoint for this 4 can be, can we have 3 as the previous index and 1 as the previous index? Yes, 3 and 1 can be the previous indices. So the maximum Fibonacci length sequence here ending at index 3 will be 3. Again for this 5, what can be the previous two indices? It can be either 4 or 4 comma 1, or it can be 3 comma 2 comma 1, right? So 3 comma 2 comma 1 is actually larger. This will make this length 4, so I'll be choosing that longer one because I want to maximize the length, right? Now ending at this 6, you can have 1 comma 5 comma 6, which is Fibonacci like, or you can have 6 and the previous value can be, let's say, 4, and you can have another previous value as 2, which adds up to this 6, right? Now you cannot add a 1 to the left of it because 1 plus 2 is not equals to 4, therefore I cannot add a 1 here. So the maximum that I can get here is 3. Now out of all these options, out of all the Fibonacci sequence ending at each of the index, I will be tracking the maximum, and that is what I will be returning. So 4 should be the answer in this case. Now in the problem, if you do not consider the seed items, that means the first pair of items, then whatever longest length that you get, you have to add a 2 value there. But if you consider the seed items, then you don't need to add it. In my code, I will not be considering this seed item, so I'll be adding 2 at the end, right? So I think what we are trying to do is clear. Now if you want to have a look at the options in recursion, then again for the same example, for 6, the previous items can range from 1 to 5, right? But you should consider that if you have a sum and you want to form an a plus b which is equals to sum, then b value, since it is strictly increasing, no two items are equal, right? There are no duplicates, therefore b has to be greater than a, and I can say that b has to be greater than sum by 2 as well. So since this is the case, therefore I can say that I cannot have an element which is less than equals to 3. That is not possible. So I can simply trim out this entire option. This will not happen as the previous item of 6. So I will just end up with 4 or 5. And depending on whichever option you choose, let's say you have chosen 5, then in this case you can only choose 1. You cannot choose any other option, right? But since your answer may not just lie at 6, but it can lie anywhere else, right? It can end at any point, because in the previous explanation I told you that the maximum value 4 was actually happening at index 4, not at index 5. Okay, the chain can actually break at any particular index. Therefore the answer can be happening at any index. So you have to keep a track of the longest length happening at every possible index and parse the entire tree. So what you have to do if you are solving by recursion, actually you have to apply a simple recursion, but there has to be a validity check in such a way that a plus b must always be equals to sum. And the height of the tree is not equals to the Fibonacci chain length. Only when the validity check passes and you make the next recursion call by including the item, then only your chain length will increase, otherwise it will not increase. So if you have a sum, it actually depends on the two previous values, the b and a, so that you can define a comma b comma sum to be a valid Fibonacci series, right? So in this case, actually there are two variables which helps you build the result. So this entire solution will depend on two variables, a, which is the previous of your b, right, and b, which is the previous of your sum value that you are trying to form. In this order, a is the smallest, then the larger one is b, and the sum is what you are trying to form, right? So this is the given order of the indices. Now all the unique subproblems therefore will be order of n square only, because a can range from 0 to n minus 1, b can range from 1 to n. So if you multiply all the combinations, it will be order of n square number of subproblem. Now in this case, in order to define what is the subproblem, if I have to say that what is the meaning of dp of 1 comma 2, what is the meaning of this? So dp at 1 comma 2 means if 2 is the end point of your Fibonacci chain length, if 2 is the end point, and if 1 is the previous item of 2, then what is the maximum Fibonacci chain length here? That will be equals to 1 plus, if you take 0 as the previous point of 1, isn't it? That means if 0 was the previous of this one, then what was the Fibonacci length ending at this point. So if the length here was equals to 2, then the length here will be equals to 1 plus that 2, which will be 3, right? And similarly, if you look at what is the meaning of this dp at 2 comma 4, if you look at dp at 2 comma 4, then if you choose 4 to be the endpoint of the Fibonacci series, right, endpoint of the Fibonacci like sequence, then it will be equals to 1 plus dp at, if you had taken 2 to be the next point and the previous point to be 1, which will be 1 comma 2, right? If they are actually forming the chain, if 1 comma 2 comma 4 actually forms a chain, this is what you can do. So in general, if I have to write it, if a plus b is giving me the sum value, then I can write dp at b and sum. That means if sum is where my Fibonacci like sequence is ending and b is the previous value of this sum, that means the b value, then that will be equals to 1 plus dp at a and b. Okay, that means if a was the previous item of b, this is the meaning of it. Now if it is not clear from here, then we can look at a dry run and it will be absolutely clear at the end. So in this case, I will be making a dp table of size n by n, and I will be just pre-filling this entire table with all 0 values, right? And I will be starting my sum value from this 3. Now I am not considering the seed values here, so 2 seed values are not counted. So at the end, the longest will be added with the value 2 and I will return it. Now let's try to solve this problem. So I told you initially that I will be applying the 2-pointer approach on the left side segment. So if I have 1 comma 2 and my target sum is equals to 3, then I will have a left pointer here and a right pointer here. I will stop until L becomes equals to R, or L becomes greater than R. So if they are actually equals to the target sum, then yes, I have found a valid previous items in the chain, right? I have found the valid previous item in the chain. So what is this? A. What is this? B, right? A and B I have found. And what is this? Is the sum value. Now if you remember what we had learned, that dp at b comma sum will be equals to 1 plus dp at a comma b. That means if we are ending my Fibonacci chain at sum, then and if the previous item is b, then this can be written as 1 plus dp at a comma b, because we know that a plus b is equals to sum. So this is following the constraint, right? So what is dp at 0 comma 1? Because a is actually the index that we are assuming. So 0 comma 1 is actually this value 0, because entire table was 0, right? So this will be 0. And if you add 1, what is this b? The b index is 1 and the sum index is actually this 2 index. So at 1 comma 2 you can fill a value 1. That is the meaning of it. And since we are done, if you update this L and R, the L will go to the right side, R will come to the left side, because if they are equal then you move them both. Okay, and then this condition will break and you will have to stop, right? So we are done with all the items ending at this 2. Now let's iterate for all the items ending at this index 3. So my sum value here is 3, right? So what is the target value? The target value is the array at sum, which is 4. Now again, my array will be 1, 2, 3, and I will be starting my index pointer at the first item and the b pointer at the last item. Now you add this 1 plus 3. Is it equals to target? Yes. So what is this? Index A 0, index B is 2. So find out again these values, right? Find out dp at AB 0, 2. dp at 0, 2 is already 0, because the entire table was pre-filled with 0 values. Now if you have to fill this B sum, what is the sum value? The sum index is 3. The B index is actually this 2, right? B index is 2. So if you have to place at 2, 3, the value will be 1 plus 0, which will be 1. Okay. Now you move both these indices left and right. So the left and right are actually pointing to the same index. That means A and B are pointing to the same index. So you have to stop here. Okay. And you are done. Now you are done with all the sequences which are ending at this 3. Now you have to see all the indices ending at this 4. So in this case, the target becomes equals to 5. And you have the sequence 1, 2, 3, 4 on the left hand side. And you start this with A and start this with B. Now is this 1 plus 4 equals to 5? Yes. What is the index A? 0. Index B is 3. So look at this dp at 0, 3. it is already 0. Okay, so dp at AB is 0. You add 1 to it and then you add it to dp at 3, and what is the sum value? Sum value is 4. So at dp at 3, 4, you add a 1 value, right? And you are done. Now you move this a to the right hand side and b to the left hand side. Now 2 plus 3, is it equals to the target? Yes, it is equals to the target. So what I have to do? A is actually index 1, B is index 2. So look at this 1 comma 2. It is already saying a length 1, right? So to this length 1, you add 1 to the current index. So what is the current index? It is 3 comma 4. So you have to always try to maximize this value. So already known value is 1. I will be trying to maximize this to a value 2 here. So I have maximized it. Now you move both of these items to left and right, and then your condition will break. Okay. Now you are done with all the series ending at this 4. Now you try with all the series ending at 5. So what is the target value? Target value is 6 here. So you have the segment as 1, 2, 3, 4, 5. And you try with the A and B value. So now A plus B value, A is actually the index, A and B are indices, right? So A's value is 1, B's value is 5. So if you add, it is equals to the target. What index you are looking? 0 and 4. So look at dp at 0, 4. It is already 0, right? And if you see that, you have to add 1 and write it here. So at what value are we seeing? What is the value of B here? So B is equals to index 4 and the sum is equals to index 5. So at 4 comma 5, you have to write 1, 0 plus 1. Okay. Now you move both of them to left and right. Again, this 2 plus 4 are equals to 6, which is the given target. So what is this index? 1, index 3. So look at 1 comma 3, it is already 0. And you add 1 to it, it is already set to 1, so no update will happen. Now you move both of them to left and right. Now since they both are equal, the same item cannot be included, and that is where we break, because this condition of while left less than r will break, right? And we are done with all the items. Now if you are tracking the longest value out of all the cells, the longest value will be 2. And once you have tracked that, since we have not counted the starting 2 values, right, the longest chain is saying that having assumed a comma b, how long can I extend it? So I can extend it longest by 2. That means if you consider the first 2 items, then it should be 4 length, and that is how you will be returning 4 as an answer. But in this case, if any extension was not possible, then the longest length would have been 0, and so you will be returning 0, right? So this is the entire approach. In this case, the space complexity is due to this table, which is n square, and the time complexity will also be n square, because we are trying to check all the possible combinations of pairs, right? So I think this is extremely clear. Let's now look at the code. In this case, we are given the array and we are given the n value. We are defining the dp table of size n by n, and dp at xy, which is the sub problem, will be the longest Fibonacci chain length ending at y, with x being the previous item. Okay, and the longest will be assigned to 0, and then I will be checking with the sum value starting from index 2 and going till n minus 1, and we will be always taking the left hand side elements as a and b. So this is the 2 pointer approach, which we have applied already on the 2 sum, and according to the 2 pointer, if the sum is less than the target sum, we increment the left pointer, otherwise we decrement the right pointer. But if the sum is equal, then we have to update the maximum of this dp at b comma sum, right, with 1 plus dp at a comma b, because we are extending the chain of a comma b by adding sum. So a plus 1 has to be added, and after that the longest will always be tracking the longest chain length, and then since the target sum were achieved with ab, you increment the a and you decrement the b. Okay, and after repeating this entire process, if you could not extend the chain length by any margin, then we return 0. Otherwise, if we can extend, then we have to also include the first seed items a comma b, and so it will become 2 plus longest. So this is the entire solution, and I hope it is clear. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of this programming videos. See you guys in the next video. Thank you.